Assalamualaikum warahmatullahi wabarakatuh. So we are going to go into chapter 4, which is on continuous time and discrete time Fourier transform. So let's go to the content. So as you see here, for the Fourier transform, we have similar to the Fourier series, which is we have the continuous time, then we have the discrete time, and also the inverse Fourier transform. So we do not have the property of Fourier transform in this chapter. So let's go directly to look at the Fourier series pair. So if you see here in this slide, we have the Fourier series pair, which is given by this transfer function, and also the Fourier transform pair, which is given by this transfer function. So if you see for the Fourier series pair, is that it's actually the summation properties we see here. So we have the summation ak ej omega t. So here is that we need if you are given the value for ak value, so find the signal for xt. So you find it using this equation, the first equation. So whereby if you are given the signal xt here, so you are going to use the second equation here. So it's given by ak. Ak is the Fourier coefficient that you have learned in the previous chapter. So ak is given by 1 over t, derivation of from 0 to t, xt e minus jk omega t. So this one is straightforward, and you have done the exercise last week. So we are going to go to the Fourier transform pair, which is given by xt and also xj omega. So xt is called the transformation pair if you want to calculate for xj omega, for xt, the Fourier transform, the signal in time domain when you are given the signal in frequency domain. So you are given signal in frequency domain, then example, the question asks, find the continuous time signal for xj omega. So you are using this first equation. And when you are given the signal in continuous time, which is in time domain, so xt here, so let's say let's find the Fourier transform or Fourier the frequency domain, Fourier frequency domain for the signal xt. So you're going to look at this equation xj omega, which is given by integral from minus infinity to infinity xt ej omega t. So the first equation is called as the Fourier transform, and the second one is called as the inverse Fourier transform, because you are going to inverse it to calculate back again to the time domain. So let's just go to this signal. So consider the periodic signal below. So you're given xt here, so which is the time domain signal. The periodic signal wave is defined over one period. So if you see later on when you look into the Fourier transform, in compared to the Fourier series, is that Fourier transform is best used when you have periodic or aperiodic signals. It means that, example, you have an odd signal or an even signal, so you can directly use Fourier transform. But in compared to when the signal is random, so you need to use Fourier series to calculate for the frequency domain or time domain. So let's go to this example. You're given xt for magnitude 1 when you have the t from between t over 4, which is here t over 4, until minus t over 4, which means that you have the magnitude 1 here. Okay, you can see that you have the magnitude 1. So since this one is a periodic signal, then you know that every t period, so let's say that you need to calculate what is the t here. So t here is given by, if you calculate, t here is given by 1, right? So when t is given by 1, then you have the periodic, the next signal is at this point, and the next signal is, for the next part, is at this point. So that is what it means by you have a periodic signal. So it's going to have the plus and minus part of the signal. And for 0 other than t over 4 means that here xt equal to 0 when you have between t over 4 to less than t over 2, right? So you have a t0 value there, right? So it means that if you plot this, you have t over 4 here, okay, and then you have t, so and then here and here you have the 0 value. Okay, so by using Fourier series, find the Fourier coefficient for xt. So now you're going to prove that either way, if you're using Fourier series or Fourier transform, you will get the same answer or the same plotting. Okay, so let's go and see how to prove it using Fourier series. This one you have learned it in the previous chapter. Okay, so let's do the Fourier series first. So you have the signal here. Okay, the signal here. So for the Fourier series coefficient, you need to use this equation. Okay, this equation. So the equation is given by ak 1 over t, integrate from 0 to t xte minus jk omega t dt. So here is that what you need to determine first is what is xt and what is the t value, right? Because since you have the 0 until t here and 1 over t, so it means that basically we need to determine what are the signals that have a magnitude value, so other than 0. So let's say you can put it like this, 0 to t, or you can put it at minus infinity to infinity, where you are taking the period of the signal. So for this case, that I'm going to use from the period is minus t over 4 until t over 4, which is this part. And then you're going to substitute into this original equation. So a naught, okay, we are going to find for k equal to 0. So a naught is equal to 1 over t, degraded from minus t over 4 to t over 4. So 1 is actually the magnitude here. So which is the magnitude of the signal itself. So this one, the magnitude. So E0, why is it 0 here? Because when k is equal to 0, then you have a 0 here. Okay, and then you get 1 over t, 1, the t over 4 minus t over 4, then you get the a naught is 0 of 0.5. Okay, then we continue to find what are the value other than 0. So the value other than 0, we are going to use the same equation, just that we are not going to substitute the k value right now. So we are going to calculate it. ak equal to 1 over t minus t over 4 until t over 4, 1 e minus jk omega t dt. So expand it. After you expand it, you are going to look at this equation here. And what you see here is that we are going to try to convert it into sine wave signal. So how to convert it to sine wave signals, that you need to have 2j at the denominator over here. So right now we don't have a 2, the value 2. So we need to multiply by 2 over 2 here. So when you multiply 2 over 2, then you will have a 2 at the denominator here. So we multiply by 2 over 2, then we write it as this equation, 2 over k omega t, expand it, rearrange it so that 2j is over here. Okay, so this equation already you can change it to sine wave signal, right? Because it's e j k omega t over 4 minus e minus j k omega t over 4 over 2j. So change it to sine signal, sine wave signal. So it will become 2k omega t sine k omega t over 4. Okay, right now we stop until here for the Fourier series. Means that we are going to calculate for the value for for k other than 0, using this equation, right? So k equal to 1, when you calculate, you will get that the a1 and a minus 1 will be 1 over 2, 1 over pi, k equal to 2, which is a2 equal to e minus 2 will be 0. And then k equal to 3, you get minus 1 over 3 pi. K equal to 4, you get the value for coefficient a4, a minus 4 is 0. And k equal to 5, you get a5 and a minus 5 is 1 over 5 pi. Okay, so after this is similar to what you did in Fourier series. You're going to plot for the magnitude phase. Since we don't have the, you see that there's no the complex value, so we don't have the phase for Fourier coefficient. So you're going to just plot for the magnitude for the Fourier coefficient. So we have this value right now, just now. Okay, let's just change the ink. So we are going to plot. So we are going to plot this Fourier coefficient. So let's go to A naught. Okay, A naught is, we calculate just now, is 1 over 2. And A1, so A1, A minus 1, you have 1 over pi, 1 over pi. And then you have at K2 is 0, so it's 0, no value. At A3 and A minus 3 is 1 minus 1 over 3. Okay, and at K equal to 4, you have 0 again. And at K equal to 5, you have 1 over 5. So actually, what you see here is that you see that for the DC term, you have a value 0.5. And for the odd value, for K equal to odd, you have a value, which is you do not have a 0 value. And for the even value, 2, 4, 6, and so on, you will have a 0 value. So when you plot, you will basically get a sinc wave if you have a rectangular signal like this. Okay. So this is to prove Fourier series. So let's next go to how to prove using Fourier transform. So from here, we just continue. This one is not yet Fourier transform, but we are going to use the signal here without getting the Fourier coefficient. We are going to try to plot this signal into a sinc sine wave. Okay, so from the Fourier series here, we are going to convert the sine wave signal into a sinc signal. So sinc signal is given by sinc theta is given by sin theta over theta. So what you have here is that you need to get the denominator for this equation, k omega t over 4, right? So what you are missing here is over 4, 1 over 4. So what you need to do is that you need to multiply this equation with 1 over 4 times 1 over 4. Then you will have this signal, right? So from here, you can already convert it into the sinc signal. So sinc, this one will get sinc k omega t over 4, and this one will be 1 over 2. So right now, how to plot this is that you already know that you have the amplitude is given by 1 over 2. So how we are going to plot for sinc k omega t over 4 into this part? So sinc, you already know that you have a decaying sine wave signal. Okay, the largest magnitude, and it's going to decay to infinity. So how we plot it is that, let's go to this page. So this page shows what the equation. So you have a rectangular, A rectangular, which is this is rectangular signal. A is the magnitude, and t over tau is actually the symbol. So A rectangular t over tau is given by A tau. So A magnitude tau sinc omega t over 2. So you have the value here. So omega t over 2 is actually represented by, sorry, I'm changing the color. So this one is represented by omega t over 2, right? So what we have here is that, sorry, no. Okay, that's not right. So we have omega t. So the t value is actually tau over 2, right? So you look at this plot. So you have the sinc value. So what you need to do is that you need to plot for A tau here. So you have the magnitude A tau, so which is this one, A tau. Then for this part here, for the frequency part, axis part, so you have determined that t value is tau over 2. So you know that the equation is given by this part. The equation, sorry, for this part, okay, the equation is given by pi over t1. So t1 is actually the period. So pi over t1. So t1 here you have tau over 2. So which means that when you substitute tau over 2, you will have 2 pi over tau and minus 2 pi over tau. So sometimes in a textbook you found out that the value is not the same with this omega, which is the frequency, omega. So you want to plot it in frequency. So omega, as you know, is omega equal to 2 pi f. And you may find out that f is equal to 1 over tau. So meaning that if you compare this equation to this equation, okay, so you will see that this equation and also to this equation, you find out that 2 over tau is actually f, and f is given by 1 over tau. So means that here is that you have 1 over tau, and here is at minus 1 over tau, is the zero value here. Right, so that is how you plot for the Fourier transform. And if you see if you see here, this plotting is quite similar with the one that you plot using Fourier series, which is, well, using Fourier series it's much more detailed, because you have the k coefficient for the coefficient value. But for the Fourier transform, you have the plot for magnitude and this at the omega equal to, mostly omega equal to 1 and minus 1. Right, so that's will be for the Fourier transform, how to prove an equation or for Fourier transform and Fourier series. So now we are going to do to the Fourier series coefficient and the envelope body. So as you see in this three graph, okay, plotting, you find out that when the t increases or the fundamental frequency omega decreases, so the envelope or sample is sample closer to each other. So it means that if you have 2 omega here, you see that the envelope is actually much more spaced out, and compared to 4 omega naught and 8 omega naught, you will have much more sampling here. So it means that you are going to have a very much more smoother signal later on. And here is a sinc function, which I already explained in the previous example. So sinc function is given by sinc theta equal to sine theta over theta. And if we see here is that the similar to sine wave, when you have the signal of omega 1 or the period of the rectangular signal for the Fourier transform is much more wider, so you will have the signal in time domain much more closer to each other compared to x3 here. So x1 and x3 is more further apart compared to x1. So we go to the next example 1. So consider an aperiodic pulse function. So aperiodic pulse means that it's not a periodic pulse, it's just one signal here. So you are given x equal to 1 from minus t over tau to t over tau, which is the amplitude A is given by 1. Right, so because the signal is a period, so we are going to use Fourier transform. Of course, you can always use Fourier series. So right now, we are going to find out what are the Fourier transform for the above signal. So what you need to do is that you need to substitute. You can always directly, substitute A equal to 1 because you are given A equal to 1. So here is that you have A equal to 1 and you have the signal is from minus t over 2 to t over 2. So we are going to use the Fourier transform equation directly. So xt omega, because we are going to find the Fourier transform, is equal to integration of minus infinity to infinity xt e minus j omega t dt. So substitute what is the value for the t value. So you have minus t over 2, t tau over 2, 2 tau over 2 here for the t. Xt, which is the magnitude here, is given by a. So of course you can change it to 1 if you like, and e minus j omega t. So substitute that, expand, then you will get something like this. So why I multiply it by 2 over 2 is because I want to try to change it to sin signal, sine wave signal. So because I need the denominator here 2j. So when you multiply by 2 over 2, you will get minus 2j omega, and then expand it some more, you will finally get the value is equivalent to xt omega a tau sin omega tau over 2. So let's say that the initial equation is that a is equal to 1. So right now is actually tau sin omega tau over 2. So this is the final answer. So we are going to plot this. So you have here a equal to 1. So tau sin omega tau over 2, and you know here directly you can take out what is the t value. So t value is tau over 2. So plot what is the magnitude a. A is tau, and then at this point is pi over t. Remember this is pi over t. So your t value is tau over 2, so you get 2 pi over tau and minus 2 pi over minus tau. So this one is you want to plot it in frequency signal or frequency omega in the domain. But if you're going to plot it in frequency f, so you're going to just equivalent it to omega equal to 2 pi f, and you get f equal to 1 over tau. So you get here, actually you found out that f equal to 1 over tau. So you're going to plot the same thing. This is 1 over tau, 2 tau, and so on. So you will get, this one is 1, this one is tau, and you have the final answer or final plotting for this signal. Right? So if you see here, the answer, the plot in this part is similar to what we have here in the example. So here is given by Vf, which is the frequency, or V omega, frequency domain, is known as the Fourier transform for Vt, and can be written as Fvt. Or you can always plot it as Vf. Right? If you want to plot it, write it as Fvt, then make sure that this F is capital, because F means that Fourier transform. For Vt is known as the inverse Fourier transform for V omega, and can be written as F inverse. So that's why it's called inverse transform. Fourier transform for F inverse V omega. So this one is just to summarize what you have learned right now. So you have learned that when you have a continuous time signal Vt, you can actually transform it into the frequency domain using Fourier transform. And also when you have the Fourier the signal in frequency domain, you can actually transfer it back again to the signal in time domain using inverse Fourier transform. So these are the equation given by the Fourier transform, and this one is the equation given by the inverse Fourier transform. So for this one is that, for example 2, is that consider the signal xt equal to e minus at ut. So for a more than 0, so what you see here is that you know that this signal is actually an exponential signal. So find xj omega. So this signal is that you are given the continuous time signal. So find the signal in Fourier frequency domain. So prove using this equation. Okay, so let's do this.